Okay guys, in today's video what we're going to be looking at is a really quick video about something called the rational roots theorem. The rational roots theorem states that if a function actually a polynomial function has integer coefficients, meaning you're not going to see decimals or fractions in this case, then they have to come from certain numbers. Now I'm going to show you what those certain numbers are with the example that we're doing, kind of take a general and a specific example through the end of this thing. So when we look at these polynomial functions, I'm going to write one up here in a second, you're going to notice that it has a leading coefficient, which is going to be a very important number, and there's going to be a constant term at the very end of the function, which is also going to be a very important term. So those are the two that we'll focus on at the beginning of the problem to set things up. We use the middle terms, like however many there happen to be, throughout the middle of the problem to figure out where am I actually going to have zeros. So we're going to find out first what are the possible rational zeros, then we're going to actually apply that to figure out what are the zeros of this particular polynomial function that I've come up with here. So our first example, which after you've gotten this written down, you can see that we use this when the degree is greater than 2 because you have great ways of solving linear functions very quickly already. You have really good ways of solving quadratic functions. Even if it's the quadratic formula, that would always work if there were zeros. So we wouldn't necessarily use this unless you're talking about a higher degree, like 3 or higher, when you're talking about a rational function, or not a rational function, but a polynomial function. So degree 3 or higher, this would be a viable thing to use. What I would like to do first, though, is give you the function. So we're going to go ahead and write the function down as I'm doing it there. This will be a good example of how to use the rational roots theorem. So let's say that our f of x was this, 2x cubed minus 7x squared minus 10x plus 24. So there's the function I've come up with. Now what we're going to do is we're going to list out the possible rational zeros first. So I'm going to highlight a couple of things here that we need to talk about. The first thing you'll notice is that the constant term at the very end of this thing is 24. So I'm going to highlight that 24 because it's going to be probably the beginning of the problem, the most important thing to look at. That is the constant term at the end. What we're going to do now is we're going to talk about all the possible factors of 24, and we're going to call those P. Like this list right here, we label it P. I'm not really sure why we call that P, but that's the pretty generally accepted term. So I'm going to list all the possible values of 24. Don't worry about a positive or a negative 24 because every one of these things, if 1 goes into 24, the negative 1 goes into 24 as well. So we're going to put a plus or minus before every one of these. And sometimes people will decide not to do that and just keep it in mind at the end. Plus or minus 1 or 2 or 3, 4, 6, 8, 12, and 24 are the values that are factors of 24 right there. So I think we got them all. Let me check real quick. I think we do. So if I missed, you can let me know tomorrow. But that's what we have right there. For the next one, we're going to look at what we call a Q. And remember I said that we're going to look at that leading coefficient. That's going to be a pretty important thing as well. The leading coefficient here is 2. And for Q, we're just going to write the factors of that leading coefficient. That leading coefficient, the only way things that go into 2, since it's a prime number, are 1 and 2. Okay? Now, let me say this. Everything that I've listed there for P, those are possible rational zeros. Those are all the whole number ones. We're also going to take each one of those numbers, 1, 2, 3, 4, 6, 8, 12, and 24, and we're going to divide them by 1. But when you divide by 1, it doesn't really change things. And since it doesn't change things, we pretty much ignore that. What we're also going to do, though, is divide each one of those numbers, 1, 2, 3, 4, 6, 12, 8, 12, and 24, and divide them by 2. And we'll get some new ones. And we're going to call everything that we list down here, we're going to list these as PRZs. So everything that was that is going to go in this list automatically, because if you divide by 1, you get that. The reason they're called PRZs is because it says possible rational zeros. And for that reason, we just kind of not have to write that every time. We're going to write PRZ. Now what we're going to do is we're going to take each of these values of P and divide them by 2, because that 2 that you see right here, that is another number right there. So that 2, we're going to divide each of them. So 1 divided by 2 is not one I've already got listed, so I'm going to write a positive or negative 1/2. But 2 divided by 2 is 1. We've already listed 1, so we don't have to write it again. 3 divided by 2 is new, so we're going to do 3 divided by 2. 4 divided by 2 is 2, already got it. 6 divided by 2 is 3, already got it. 8 divided by 2 is 4, we've already got it up here listed with the p's. 12 divided by 2 is 6, great. And 24 divided by 2 is 12, so that one's already listed up there as well. So all my possible rational zeros, I'm going to highlight up here in this little green color and see if this shows up at all. All of these numbers that we said at the beginning are possible rational zeros, as well as these. Now 1 and 2 you'll notice are already in the list of P. We didn't highlight the Q's though because those do not determine whether it is or not. So these are the possible rational zeros right here in the green. How do we use those now is the question. And for that we're going to use some synthetic division that you've learned about a couple weeks ago. So when we look at these numbers, and these are the terms right here for f of x. I'm going to go ahead and copy down the coefficients from the coefficients only. 2x cubed, negative 7x squared, negative 10x, and 24. And what I'm going to do, instead of having this whole, instead of setting up a synthetic division thing every time, remember when we talked about synthetic division in the first place, we were looking for remainders of 0. And since I'm looking for remainders of 0, I'm going to set up this little thing right here. I will tell you it's easiest probably to start with a 1 and just go through. So let's see how this will go. If we put a 1 in here, the way we're going to handle this is we're going to say, we always just drop down that first number right there. So there's a 2 at the beginning, this column's going to say 2. Now we do 1 times 2, which is 2, and add that 2 to negative 7, which is negative 5. We do 1 times negative 5, which is negative 5. And negative 5 and negative 10 gives us negative 15. We do 1 times negative 15, negative 15, add it to 24, and we get 9. That gave us a remainder that was not 0. So what that told us is that 1 is not a rational 0 in this case. What it also tells us is if we put a 1 in, because of the whole idea there, if we put a 1 in for x and substitute an x into the function, we would get a 9 for an answer. So it can help in that respect to kind of narrow things down. We know that the point 19 would be on the graph of our polynomial, and that might help us down the road. We don't have to list that every time. I just wanted to do it there so we could reinforce that idea. I tried negative 1. We go through the same process, drop down the 2 from the beginning. We're done with this first line underneath there. Negative 1 times 2 is negative 2, and that combined with negative 7 is negative 9. Negative 1 and negative 9 is 9, and then when you do 9 and negative 10, you get negative 1. Negative 1, negative 1, when you multiply those, you get 1. Add it, you get 25. So what that tells us is at negative 1, we get the value 25. That's even further from 0 than what we started with. Like on the last one, we were at 19, now we're 25 units above. So that's not going to be it. I've kind of exhausted the idea of 1 now. It doesn't work anymore. So we're going to go on to 2. When we go to 2 and try that one, because that's the next thing I had listed in the P, you put down that 2 from the beginning there, from the top down to here. 2 times 2 is 4, and negative 7, when you add that, you get negative 3. 2 times negative 3 is negative 6, along with negative 10 is negative 16. And then negative 2 times negative 16 is negative 32. Add that to the 24, and you get negative 8. So that gives us 2, negative 8. I would want to point out something here. Look at 1, 9, and 2, 8. This is going to be something that might help us if they're really complicated looking problems. The fundamental theorem of algebra tells us that we have to go, if we're going from 9 to negative 8, that we have to go through 0. So there is a 0 somewhere between 1 and 2. That's not a guarantee that's a rational 0, but it is a guarantee that there is a 0 in between the two of them because polynomials are continuous. They have that nice curve. They don't jump around or anything like that. Let's go ahead and try negative 2 now because I know that one works and I want to move it on. So we put a negative 2 in. I'm going to drop down to 2. Negative 2 times 2 is negative 4, and negative 4 and negative 7 is negative 11. Negative 2 times negative 11 is 22. 22 plus negative 10 is 12. And then finally, negative 2 times 12 is negative 24. Negative 24 and positive 24 gives me that remainder of 0. So we have found that point, negative 2, 0, and that is an x-intercept, which is what we were looking for. What I'd like to do beyond that now, let's talk about what we've actually found. We have found that x equals 2 is a solution or a root. So it's a solution to f of x equals 0, or a root of f of x. Now, what that leaves us with, because we started with a cubic equation, whenever you do synthetic division, you might remember that you have reduced the power of the function by 1 to get your quotient. Your quotient in this case then, since it's got a 2 right here, we've got 2x squared minus 11x plus 12. And remember, we're still trying to find out where the roots are, so this is going to equal 0. When we look at this one then, we have better ways of solving this when this equals 0 than to do this rational roots theorem, because you can see it's guess and check. It's an educated guess and check, but it's still a guess and check. So what I'm going to look at with this case is we can factor the 2x squared minus 11x plus 12. So once we get down to quadratic, something we can factor, let's work with that. I know it's going to have to be this, and let's see if I can remember what I had here. I think we had a -4 and a -3. And the reason that works, that's -3, that's -8, so altogether it gives us the -11. If you solve each of these two pieces separately using that zero product property, you're going to end up with x equals 3/2 and x equals 4. So my three solutions for this cubic equation are -2, 3/2 or 1.5, and 4. Go back to this real quick. We said that there would be a solution or a 0 somewhere between 1 and 2, and you'll notice that there was one at 1.5. So it went from 9 to -8. It had to go through 0 to get there, and that happened when x equals 1.5. So that's one example of the rational roots theorem that you guys are going to be applying in class. We'll talk about some special exceptions and things like that as we get to them in class, and that's why we'll have some time in class to work on this. You have a couple of problems there that I would like you to do tonight on your assignment sheet, so if you can try those, have those ready to go for tomorrow morning. You're going to find them very similar to this one, just to give you a little bit of practice with picking out the P's and the Q's and the PRZ's, and then we'll see what we have to review tomorrow in class with those. So if you have any questions, you can rewind and watch again, and then in class tomorrow we can go a little bit deeper. Thanks for watching. See you tomorrow.